We have discussed before that one way to evaluate the quality of a synthesized mechanism is to check the transmission angle of the mechanism. In this module, we will define the notion of transmission angle and learn how to compute the transmission angle of a mechanism. The transmission angle of a mechanism at a given value of the input angle θ2 is defined as the absolute value of the acute angle between the output link and the coupler. More mathematically, alpha at a given angle θ2 is the absolute value of the difference between θ3 and θ4. Furthermore, if alpha or the difference between θ3 and θ4 is less than or equal to pi by 2, then we have mu or the transmission angle at θ2 equal to alpha, and if alpha is greater than pi by 2, then the transmission angle is pi minus alpha. Now let us look at the picture on top. The transmission angle is this angle here or the angle shown here, and in this case the transmission angle is acute. However, if my picture looked like this, where this was C, this was D, and this was O4, the transmission angle would have been this angle mu and not this angle, which is bigger than 90 degrees. The takeaway point is that the transmission angle of any mechanism for a given value of the input angle θ2 is always between 0 and 90 degrees. This is by definition. Transmission angle of the overall mechanism, which we denote as mu star, is the minimum of the transmission angles for all possible values of the input angle θ2. For each feasible value of θ2, we will get one value of mu, and if I take the minimum over all the possible of θ2's, that is my mu star. Note the difference in the definition in the second bullet point versus the first bullet point. When we talk about the transmission angle of a mechanism, we are interested in mu star and not mu. Why is the transmission angle important as a measure of quality of a mechanism? Transmission angle allows you to measure the quality of force transmission from coupler to output link. So let us look at the picture on the top right here. The force that comes from the coupler CD onto the link DO4 is F34. The moment of this force actually rotates the output link. The force F34 has two components. One is along the link 4, the other is perpendicular to the link 4. Since this angle is mu, the component of F34 along the link 4 is F34 cos mu, and the component perpendicular to the link 4 is F34 sin mu. Therefore, the moment acting on the link 4 that rotates the link 4 is C times F34 sin mu. Now, as mu tends to 0, the magnitude of this moment that rotates the output link tends to 0. So a lower value of the transmission angle means that the quality of the mechanism is lower. We usually prefer higher values of transmission angle. Higher values of transmission angle means that it is easier to rotate the output link for the same value of F34. Now let us look how to compute the transmission angle of a mechanism. So first, we will look at the computation of transmission angle for a given input angle θ2. So let's look at the picture on the left. This angle is mu. This is my angle θ2 as marked here. The link lengths are A, B, C, and D. I join A and O4 and let H be the length of AO4. So using the law of cosines from triangle AO2O4, I have H square equals to A square plus D square minus 2AD cos θ2. From triangle ABO4, I have h squared equals to b squared plus c squared minus 2bc cos mu. Therefore, the right hand side of this equation and the right hand side of this equation are the same. That's what we have put in here. From here, just by rearranging, so taking these terms to this side and dividing throughout by minus 2bc, we get an expression of cos mu in terms of cos theta 2 and the link lengths. In the previous slide, we defined the transmission angle as the absolute value of the difference between theta 3 minus theta 4. However, when we worked out the formula for the transmission angle, we see that it is not dependent on theta 3 and theta 4 explicitly. It is just dependent on theta 2. So if you just know the input angle, you will know the transmission angle for that particular value of the input angle. For a double rocker mechanism, the coupler is a crank. Hence, the coupler undergoes a full rotation. So, the coupler during the motion will align itself with the output link and also be at an angle of 90 degrees to the output link. Therefore, the minimum and maximum transmission angles that are possible are 0 and 90 degrees. Since the transmission angle of a mechanism is the minimum possible transmission angle over its full motion, the transmission angle of a double rocker mechanism is 0. So what happens when transmission angles become 0 or very small? Then there is no moment that can move the output link. So the mechanism may get jammed. In other words, the mechanism may not move. Now, we will use this formula to find the transmission angle of a mechanism that is driven by a crank. So I've written down the formula here that we had in the previous page. One thing to note here is except for theta 2, which varies as the link moves, all the other variables here are constants. They are the link lengths. Once you have designed the mechanism, they don't change. Therefore, cos of mu will have its extreme values wherever cos theta 2 has its extreme values. So what are the angles at which cos of theta 2 takes extreme values? Theta 2 equal to 0 is where cos of theta 2 equal to 1. That's the maximum value that cos of theta 2 can have. Theta 2 equal to pi implies cos of theta 2 equal to minus 1. That's the minimum value that cos of theta 2 can have. So cos of mu will have its extreme values either at theta 2 equal to 0 or theta 2 equal to pi. So when theta 2 equal to 0, cos of theta 2 is 1. So we have b square plus c square minus a square minus 2ad plus d square by 2bc. And the term in the parenthesis here is a minus d whole square. So we have b square plus c square minus a minus d or d minus a whole square, it doesn't really matter, by 2bc is cos of mu. So mu equals to arc cos of this expression here. When theta 2 equal to pi, cos theta 2 is minus 1. So we have cos mu equal to b square plus c square minus a square plus 2ad plus d square. So mu equal to cos inverse b square plus c square minus d plus a whole square by 2bc. Because this term in the parenthesis here is d plus a whole square. Now geometrically, when theta 2 is equal to 0, we have links 1 and 2 as collinear and overlapping, as shown on the picture on the left here. When theta 2 equal to pi, we have links 1 and 2 as collinear, but they are not overlapping, and it is shown by the picture on the right. Now once you have obtained this gamma 1 and gamma 2, you have to be careful to make them within 90 degrees. So if gamma 2 is less than equal to pi by 2, then mu 2 is gamma 2. Otherwise, mu 2 will be pi minus gamma 2. And the transmission angle of the mechanism will be minimum of mu 1 and mu 2. Why? because these are the two extreme values of mu. So I don't really need to take into account any other values of mu, just these two extreme values. And this formula is valid for both double crank and crank rocker mechanisms, with the caveat that the crank is the input. For a non-Grashof mechanism, the minimum transmission angle is always 0. Why? Because for a non-Grashof mechanism, the output link and the coupler always align during the motion. In other words, they come into a toggle configuration during the motion. The figure on the left shows the configuration of a triple rocker mechanism where the transmission angle is 0. The figure on the right shows the transmission angle at the other toggle configuration where the input link and the coupler are collinear. Note that in this case the transmission angle may not be 0. However, the overall transmission angle of the mechanism is 0, or mu star is 0. Let us look at an example for computing transmission angles. We will look at the same example that we looked at for the 4-bar mechanism with the same link lengths. First, what we will do is find the transmission angle of the mechanism at theta 2 equal to 40 degrees, and then we'll find the transmission angle of the mechanism over its whole range of motion. So let's look at the solution to part 1. I am writing down the problem data, the value of the sides A, B, C, and D, and I have written them down in the units of meters, and theta 2 is 40 degrees. I can substitute all this data in the expression for cos mu, and I'll get the value on the right hand side. If I do cos inverse of 0.7984, I get mu, or the transmission angle, at the angle theta 2 of 40 degrees as 37.02 degrees. Now let's verify that this makes sense with the first principles definition. Because we had solved the position kinematics problem before, and we had obtained the following values for the angles theta 3.1, theta 3.2, theta 4.1, and theta 4.2. So from the definition, my transmission angle will be theta 3.1 minus theta 4.1, and I have to take the absolute value, which will be 37.02. I can also do mu equal to theta 3.2 minus theta 4.2 and take the absolute value, and again the angle comes out to be 37.02 degree, which matches the answer I got from the formula here. What does this say? This says that whichever solution you pick doesn't affect the transmission angle. And this should be obvious because transmission angle is only dependent on theta 2, and theta 2 has a single value. Theta 3 and theta 4 may have different values, but the difference of their absolute value is always the same. Now let us compute the transmission angle of the mechanism over the whole range of motion. Again, I have written down the link lengths. First, you need to recognize that this mechanism is a Grashof crank rocker mechanism. Why? Because the smallest link here is A, the largest link here is B, 0.12, and if you add them you get 0.16, which is less than C plus D. So it's a Grashof mechanism, and since a link adjacent to the smallest link, which is the link with link length T, is the ground, I have a crank rocker mechanism. Furthermore, I have said that my input is the link with length A, so my crank is the driven link here. Therefore, I can use the formula that I derived before, which is shown here. Repeating the same argument that I had before, extreme values of mu will occur at extreme values of cos theta 2. That is either at theta 2 equal to 0 or at theta 2 equal to pi. At theta 2 equal to 0, cos theta 2 equal to 1, and cos mu is equal to this expression here, which gives rise to this value on the right hand side. And if I do the cos inverse, I get the value of mu1 as 26.38. Similarly, at theta 2 equal to pi, I have cos theta 2 equal to minus 1, and I get cos mu2 equal to 0.06. I solve for mu2 by taking the cos inverse of this value, and I get 86.42. So my transmission angle here is 26.38 degrees.